in our last part, we discussed the abstract Fourier series and Fourier coefficients. We have a vector space equipped with an inner product so that we can talk about orthogonal relation, and also we can define the orthonormal systems. Then, given a vector in the space, we can construct the Fourier coefficients and then Fourier series. Okay. Now we go to our concrete situation. That is, we will study the concrete functions. As we know, many vibrations phenomena in nature has periodic feature. For example, the vibration of a stream. So this phenomena can be described by periodic functions. But periodic functions can be very complicated. And the sine and the cosine are the simplest periodic functions. So a natural question is that, can we express a general periodic function into the sum of the sine and the cosine? Can we consider a general vibration to be the total effect of the simplest vibration described by sine and cosine? So, in other words, suppose f is a periodic function. Suppose it's 2 pi periodic. We want to express this f into the sum of sine and cosine. That is fx Okay, this is our purpose. Here, AK and BK are real numbers, the coefficients. So, any 2 pi periodic function is completely determined by its value, by its definition on an interval of length 2 pi. For example, if you define a function minus pi to pi, you define a function in this way. Then you can extend the function 2 pi periodically to obtain a new function. This function is defined in the interval 2 pi and pi. Then you can extend the definition periodically to obtain a function defined over the whole real axis. So you have difficult. Extend the definition to the whole real numbers. So we assume that our we only need to give the definition of f in the interval minus pi to pi, or any other interval of length 2 pi. Okay. Also, we will apply the integral as our tools to study this problem. Therefore, we need to assume that f is integrable, and we allow the singularity. So f might be unbounded. For unbounded function, the integral is considered as the limit of approximated integral. So let's call the f AB. If f is AB, f defined on AB is integrable on AC for any C, then the definition of the integral of f on AB is the limit C goes to B. Okay, and if the limit exists, we say that f is integrable over AB, and if the absolute value of f is is make sense, that is converge, we said f is absolutely integrable. This is equivalent to require that this integral is finite. Okay, so f is absolutely integrable. Okay, so we require f is at least absolutely integrable in this sense. The function might be unbounded. The integral is considered in this sense, taking limit. And if after taking absolute value it is integrable, we said it is absolutely integrable. Okay. And also we denote all the such function by the L, or absolutely integrable function 1 minus pi to pi. Okay. And sometimes we also consider the function which is square integrable. Square integrable. That is 2 pi f square. This is finite. That is, after taking square, the function is integrable. Such a function is denoted by L2. That is, all square integrable function 4 minus pi. Okay, so we will mainly work with these two classes of function, absolutely integrable and square integrable. Now we consider L2 first. Consider L2. Under the usual addition and multiplication, scalar multiplication, this is a vector space. That is, f plus g is a new function whose value at x is fx plus gx. So if f and g are square integrable, then so does the sum of f plus g. So if f and g is L2, then f plus g also in L2. Therefore, you can define the addition in L2. If for some f and g in L2, the sum is not in L2, you cannot define the addition in L2. Fortunately, this is true. Why this is true? It is simple. Minus pi f plus g square, that is minus pi f square plus g square plus 2fg. Then this is the f square plus g square. Because this is finite, we have the Cauchy-Schwarz inequality. Fg, the absolute value of Fg will not greater than f square g square. Okay, so using this, and f and g belongs to L2, so this is finite. Therefore, the integral of this term makes sense and will not greater than will not greater than I have no space to write. Anyway, this is a finite number. So this means that f plus g square is also integrable. So that is f and f plus g belongs to L2. So we have an addition in L2. Similarly, lambda f also in L2. If f is L2 and the lambda is a real number, so L2 is a vector space. Okay, in this vector space, we can introduce a inner product. Inner product. The inner product is defined in this way. For f and g in L2, the inner product of fg is 1 over pi minus pi fg dx. So as you can check, this satisfies the requirement of an inner product, except that f is 0 does not mean that f is the zero function. This is the only violation of the definition of the inner product. But if we consider the two functions, we identify the two functions which are different at a very, very small amount of points. That is, if we identify the two different functions as the same function. If we identify f and g in case f not equal to g is very small, is of measure 0. Measure 0. Roughly speaking, this means that f almost equal to g. They are different at maybe, for example, f finitely many points, because changing the value of the function at a very small amount of points does not affect the integral. So we cannot expect that the integral of f squared is 0 to get f identically 0. At most we can expect is that f is almost 0. Then we identify the two functions almost identical to be equal. In this manner, this is really an inner product, as you can check. Fg equal gf, and f lambda g plus h is lambda f g plus fh. Okay, so the other requirement of inner product are true, except this one. The reason is that changing, for example, finitely many points, changing the value of f at finitely many points does not affect the integral. This is the reason. But if we identified two functions which are almost identical, that is, the point where they are not equal consists of a neglectable set. That is what we call the measure 0. But we could not give the precise meaning of this terminology. Okay, so in this way, this is really an inner product. Okay, so we should not be so legal here. So L2 consists of functions f defined minus pi to r, such that f squared is integrable, and which the inner product we just defined. Which this inner product, this is an inner product space. Inner product space. And we can take an also normal system. Once we have an inner product space, you want to take an orthonormal system. Okay, so maybe we use this system. This is an orthonormal system in our space L2, as you can compute directly. This is a simple computation. For example, you will see that 1 over pi minus pi to pi cosine kx dx, that is 1, and minus pi pi sine kx, that is also 1, and but minus pi pi cosine kx sine lx, that is 0, as you can compute it, as you can compute and verify this statement. So the result is that this is an orthonormal system in L2. Having obtained an orthonormal system, our previous abstract argument applied. Once you have an orthonormal system in an inner product space, for every f in the space, you have the Fourier coefficients, and you also have the Fourier series. Okay, so apply this abstract result to our precise situation. We know that f has a Fourier series that is maybe that is the ak cosine kx plus bk sine kx. Okay, f can be we can construct the Fourier series of f.